Yeah, thank you so much for the introduction. Good morning, everybody. My name is Christoph Bleicher, and I'm Director of the Division Structural Durability, working at the Fraunhofer Institute for Structural Durability and System Reliability, LBF, which is located in Darmstadt, more or less in the mid of Germany. I want to present some recent results that we gained on within a large Fraunhofer internal research project together with colleagues from Fraunhofer IWM and IGCV, dealing with the influences of recycling aluminium, specifically on the aluminium silicon material, when we look on quasi-static and cyclic material data. This complete process and the research results are embedded in as I said, Fraunhofer internal research project called Future Car Production, where we strive to take a deeper look into new modern ways of producing car body systems. We are talking about gigacasting, we are talking about structures that need to be somehow sustainable, that need to be produced from recycling aluminium from scrap material on the one side, but need to be dismantleable, need to be repairable, and so on. So within this project, we take with 8 different institutes a deeper look in improvements in the production of car body systems, with a focus on efficiency, sustainability, and also availability. This is more or less an holistic approach, and within this approach we now focus here, and that's the topic of my presentation, together with some institutes, on the influence of recycling aluminium and recycling fractions on the lifetime of the fatigue strength of components. Getting to know what are implications from the recycling material on the lifetime, and also on the lifetime assessment of components later on, to hopefully improve things like lightweight, to improve material optimization and material utilization. So when we look a bit deeper into the specific sub-chapter and topic, we worked here on, as I said, an aluminium silicon manganese alloy produced with gravity casting. And at the end, when we talk about recycling and reuse of aluminium, we might have the problems that we have during the recycling process, additional fractions of iron that will gather in the recycling aluminium. We will have problems with copper and zinc that due to the recycling process and will gather in the recycling alloys. And the question is, how many effort do we spend, or what we can spend in terms of CO2 emissions and so on, to clean up those alloys on the one side, or leave them as they are, because we can prove that the fatigue strength and integrity of a component at the end can still be met. So it's a lot of influences from melting, from refining, and what we did in this case was concentrating on gravity casting, which is produced in a chill mold. What we see on the left side is here the chill mold, or the product, the casting at the end, produced in the chill mold, where we have the runner and the riser system of the casting system, and we removed some specimens, some round specimens from this chill casting. We now concentrate in this presentation on unnotched specimens on the one side and 2 notch geometries on the other side, trying to see what is happening at the end with the fatigue strength, and what are the results under the different stress concentration factors. Before we went into the manufacturing process and into the fatigue testing, we had to decide what do we want to add to simulate a recycling aluminium alloy. And so we went for a primary alloy that is available on the market, which is an AlSi7Mg0.3. And then we decided to add in one secondary alloy, what we call it in this syllabus here, where we added 0.5% of iron and 0.25% of manganese, and then a secondary 2 where we added to those 2 addings copper and also zinc. For sure, we made some quality assurance. So colleagues from other Fraunhofer institutes made some scans, X-ray inspections, CT scans, to see what are the implications from the primary to those secondary alloys in terms of defect assembly and defect distribution. What we got to know at the end from those results most of those situations and materials were flawless and the components were comparably sound, and we could not really see that from the secondary alloy, and those effects of iron or manganese will add an additional factor of defects in the microstructure, which is good, and was the first proof for us that it can work to use recycling aluminium. When we look on the quasi-static material data and the results, we made 2 attempts. We wanted to see on the first side what is the basic data, and what we see on the left side is a result from 6mm tensile test specimen, 6mm in diameter. And when we compare those results, we see the dramatic loss in the elongation, which is mainly related to the iron content. And we could see that for this secondary 2 alloy, where we had additionally copper and zinc, that we had a slight increase in the tensile strength. But the main result here was we have a reduction in the elongation at break. On the other side, we made the same tests with a larger specimen to account for some size effects. The results were comparable, so we could not see, at least in this region, that we have a strong influence from size effects coming from the specimen. Coming to the fatigue tests, we made stress and strain control fatigue tests, stress control tests until 10 to the power 7 cycles for alternating and tensile loading to get information from the notch effect. We had test frequencies around 90 to 115 hertz and made the evaluation according maximum likelihood. And without that, we made the strain-controlled fatigue tests and the range up to 10 hertz. We made the evaluation basically on Koffemans and Baskin and Morrow, but with a trilinear approach. This accounts a bit, I don't want to go too into detail in this approach, but we see that sometimes this trilinear approach empowers and improves the compatibility between the strain life and the stress life curve. At the end, what do we do here in this approach? We separate the elastic fraction of the strain life curve in 3 parts, and especially account for the fact that we have in the stress controlled area here around 10 to the power 6 cycles something like a knee point, which is classically not incorporated in the tests and in the evaluation according to the classic approach from Koffemans and Baskin and Morrow. When we look at the results, we start with the stress-controlled fatigue tests. You see at the end, the main takeaway from this picture here is that we see on the upper side here the alternating loading results, the tensile loading results here beneath that for the unnotched configuration. And roughly we can state the real large difference between the fatigue strength for the secondary alloys and the primary alloys is not really large. What we could see beneficially is that when we come to the secondary, and sorry, there's a mistake, the secondary 1 and secondary 2 mean stress sensitivity, that we got a loss in the mean stress sensitivity, which is beneficial on the one side. And looking at, for instance, the secondary 2 alloy, we had here a secondary 1 alloy, we had a lower slope in the medium cycle fatigue range, which is also beneficial when it comes to damage sum accumulation. Even in the tensile loading, we could see a slight improve. This might be a bit related also to the scatter band, but nonetheless, it seems that the secondary alloys, due to the iron and copper content, improve in the tensile loading regime a little bit in fatigue strength. So we could not see that there is generally a loss in fatigue strength for those alloys. The same works for, it shows the same result for the results under the notch configuration. So we have here in those 3 lines the results for the comparably smooth notch with a stress concentration factor of 1.72, and in relation to that, here the SN curves for a stress concentration of 2.5. We see at the end notches are equalizers to fatigue strength and material strength, so that's what we see here. Not really something surprising when we compare the unnotched specimens and go over to the notched configuration. What is remarkable is that the scatter bands are comparably low. Okay, we did not test 50 specimens for each SN curve, but nonetheless, we see that the different scatter bands that we derived here are comparably low, especially when we keep in mind that usually for a cast material, we would tend to have something like a T sigma of 1 to 1.3. There we are have really good results in this case. Let me go over to the strain-controlled fatigue tests. You see, first of all, the primary alloy. What we can state here is that we have a strong cyclic hardening effect. We see here the stress-strain curves from the evaluation of the test results in comparison to the initial loading curve, and we see a strong cyclic hardening effect. And this was present for all those alloys, but the strongest effect more or less came here from the primary alloy. And you see on the right side the evaluation on the strain life curve with this trilinear approach, where we accounted the first step here a knee point in this regime. In this area, and additionally we included also the points from the stress control test from the unnotched specimens in this evaluation to get it a bit more stable, especially in this area. Beside 10 to the power 5 cycles, we can state that we have more or less a pure linear elastic material behavior, and so strain and stress is only the difference is at the end the Young's modulus. And so we used those test results here for a better and more substantial evaluation. When we go over to secondary one, we see that on the strain life curve, we are something like a flattening, and I'll show you in 2 slides the comparison between those curves. At all, we see, especially in the low cycle fatigue regime, some flattening. This comes from the reduction of the elongation at break, for sure, that we could see in the quasi-static data. And on the other side, a bit an increase in the elastoplastic regime when it comes to the scatter band of the stress strain curve and also the strain life curve. Cyclic hardening is present here as well, but the effect is not so strong due to the fact that we have, in any case, for the secondary 1 and secondary 2 alloy, we have a bit higher tensile strength and a higher slope for those tensile test results. Secondary 2 was not really surprising, more or less the same results. When we look into the comparison of those curves, primary, secondary 1, secondary 2, we can state that we end up in the stress strain regime more or less in the same region. When it goes over to higher total strains, then there is a bit more performance in the primary alloy, and so we see it also for the strain life curve. So in the strain life curve, we see that we have some number of cycles more to failure in the low cycle fatigue regime. So as I said, the elongation at break and the higher ductility plays a role here also in the evaluation of those strain control tests. When we look a bit in the microstructure, we made some evaluations, or more precisely the colleagues in Munich did, and when we compare those results, we have the aluminium, the silicon in the 2 main phases. The copper in the last secondary 2 alloy is somehow incorporated as a solid solution phase in the matrix. And when it comes to the secondary dendrite arm spacing, it was not really surprising. The values were comparable. And usually the dendrite arm, or the secondary dendrite arm spacing more precisely, is the value that we somehow try to use for a comparison to the fatigue strength. Yeah, since we see not really a large difference in the secondary dendrite arm spacing and not in the fatigue strength, this somehow matches once again also for those primary and secondary alloys with that what we know from literature. When I summarize my presentation, I hope I could give you a bit an overview about this future car production project, and specifically now about the fatigue strength evaluation of this aluminium alloy. What we are now working on is to go for an AlSi7Mg for high pressure die casting. A lot of components are produced in high pressure die casting in automotive industry, and this is what we are currently doing. What was for us somehow surprising and benefit in performance, I would say, is that we don't need to be afraid for recycling alloys, especially even when we have higher fractions of iron and copper. So the results prove for us somehow with a rule of thumb that we have comparable fatigue results for something like the primary alloy and the additional ingredients that we have here with copper, zinc, and so on and so on. I would rather say that we have a bit an improvement of the data. You saw that the slope for the secondary one improved a little bit, got a bit flatter. We have comparably low scatter bands, and the mean stress sensitivity is also reduced while adding those iron and manganese fractions. So and I showed you also the cyclic hardening effect, that we lose a little bit in the LCF regime. This might be interesting in most cases, I would guess. We're not talking about a high elastoplastic loads on the car body parts when it comes to a total strain of 2 or 1.5% total strain. So overall, we could not state that we have really a problem with this alloy with adding some material, some elements here, and we could give a good estimate, I would say, for further developments in the direction of secondary alloys for aluminium. Yeah, then last but not least, I want to thank you very much for your kind attention this morning, and I'm open for questions. Thank you so much.